In the last video, we started talking about the method of undetermined coefficients for finding a particular solution of a linear, non-homogeneous, constant coefficient differential equation. Let me review a couple of the ideas before we go on. We're solving at the moment equations that look like that. Constant coefficients, non-homogeneous. And we learned last day that a general solution of this is composed of finding a general solution of the associated homogeneous equation and add to that a particular solution of this non-homogeneous equation. So we were concerned with finding the particular solution because we found out how to find a general solution of the associated homogeneous equations 2 videos ago. And we're talking about this method called undetermined coefficients. And we did some examples, and at the last of the video, I gave you this rule for finding a particular solution using undetermined coefficients. And again, it only handles powers, exponentials, sines and cosines of these forms, or sums or products of. So let's put an example up here, not follow it, right? All right, saying what is form for y sub p if you've got phi of d operating y is equal to x squared minus x squared cosine, let's make that one x, cosine 5x plus e to the x sine 2x. Suppose that's the right-hand side, and we want to write down what the form is, and I'll tell you why I want to solve in a minute, right? So y sub p would be what rule 1 says. For each term, this one, put a constant in front of it. Then differentiate it. If you get anything new, put a constant in front of that. And new meant linearly independent. If you differentiate x squared, you get 2x. That's different. If you differentiate x, you get 1. That's different. So you have that. Let me also put it here, say minus 5, just to make a point. So I just took care of the x squared. I don't have to take care of the minus 5 because it's taken care of in the C. So any polynomial that's sitting there, when you take care of the highest power, you automatically take care of the lower powers. All right, on to the next. We have an x, cosine 5x. So we would put dx cosine 5x, a constant in front of it. Then we differentiate that and look for new things. If I differentiate this, I get that one times that one. That gives me x sine 5x's. That's new. So I put e to the x sine 5x. In addition, if I differentiate this, I have to differentiate that x with the product rule, and I get that. That's different than what's there now, and that's different than that. I need an f, cosine 5x. Done with you. Now I got to differentiate him. If I differentiate him, I take this one times that one. That gives me x cos 5. I got him. But I also get this one times this one, which is sine, and I need that one then, g sine 5x. I now differentiate this one, but it gives me that one. I differentiate that one, it gives me that one. I'm done with this guy. I have 1 to go. I'm up to h. E to the x sine 2x. I need to differentiate this. This one times that one gives me cosines. I need that. Plus j e to the x cosine 2x's. I take this one times that one. That doesn't give me anything new. Okay, you're done with it. Now I differentiate u. U times derivative of u, that's him. Him times derivative of him is him. I'm done. So there's the form of my y sub p. How would you like to pick that up and put it into here and equate coefficients and end up with 9 equations and 9 unknowns? You would have 3 equations in these 3. You would have 4 equations in those 4, and you would have 2 equations in those 2. All right? But that tests, that kind of question, tests whether you understand Rule 1. I pointed out at the last day's video that Rule 1, because it's called Rule 1, it doesn't always work. There's going to be a Rule 2. To illustrate, suppose I gave you this nice, simple little differential equation. That. Now that is homogeneous. No, I don't want that one. Sine 2x. If you were to follow rule number 1, it would say, assume y sub p is equal to a sine 2x plus b cosine 2x. Great. Cos in front of this one, differentiate that one, you get that one, differentiate that one, you get that one. So now you substitute it here. What do you get? Minus 4a sine 2x minus 4b cosine 2x plus 4a cos 2x b sine 2x equal to sine 2x. And you might have already spotted there's a problem. All right. Whoops. I'm differentiating twice, yes. Oh, I wrote these guys down the wrong order. Okay, that was supposed to be a sine. And this one is supposed to be a cosine. All right, that was a problem you already spotted too. Now that I corrected that, do you see the real problem? Well, this one cancels that one, and this one cancels that one, and so we end up with 0 is equal to sine 2x. What we were hoping for was 2 equations and 2 unknowns, and they didn't come. Well, if you're really astute, you could have said, I could see that happening, Trim. You didn't have to do that. I could see it happening. Suppose you went and looked at the homogeneous equation. Now, by now, if you studied enough work, you can say, I can solve this in my head, or just by spotting it. Or you can say the auxiliary equation is m squared plus 4, plus or minus 2i. Therefore, y of x is equal, let's call it y sub h of x, is equal to c1 cosine 2x and c2 sine 2x. That's a general solution of the associated homogeneous equation going through the auxiliary mentally or just looking. But notice that's the same as that. It's just got different names in front of the functions. C1 and C2 instead of A and B. And what do you know about this? This is a general solution of that. So if I put this here, I'll get 0. If you put that there, you're going to get 0. And you did. So rule 1 is not working on this example. So we're going to have to modify. We're going to have to pick a different y sub p. A different one. So the question is back to intelligent guessing. What else might you guess at? So if you put it here and you put it here, you might get sine 2x when you're done. Well, I'm not going to switch to polynomials, and I'm not going to switch to exponentials. It's got to be these tricky guys, because you've got to end up with sine 2x. Well, if I thought when I went through and I went into homogeneous stuff, maybe you need an x in here. Maybe you need an x in there. Now, I can only find out by trying. If it works, great. If it doesn't work, I'll try something else. So we say substituting. What do we get? The second derivative, a. Second derivative of this, let's use that rule. Second derivative of him times him, gone. Twice the first derivative of each. 4 cosine 2x. Differentiate that once, differentiate that once, and done. And then him, x, times the second of him, minus 4 sine 2x. How does that look then for the second derivative of that? Rather than using multiple power or product rules. On to the next, we need the second derivative of this guy. B. Same rule. Second of him, gone. Twice the first derivative of each. How about minus 4 sine 2x? Then plus him times the second of him, minus 4 cosine 2x. How's that then for the second derivative? After that, then we need 4 times the first derivative. A sine 2x plus 2ax cosine 2x plus b cosine 2x minus 2bx sine 2x. Why am I taking the first derivative? I don't know. There's no first derivative here. So 4 times him. Ax sine 2x. Bx cosine 2x. It's supposed to be equal to sine 2x. Equating coefficients. But let's take a look first. Oh, notice. They're the same, except one's positive, one's negative. They're gone. Notice. They're the same. One's positive, one's negative. So they're gone. What's left? Cosine 2x's and sine 2x's. Cosine 2x's, 4a of them there. That's all. And there are none on the other side? 0. And sine 2x's, there's minus 4b of them here. And on the other side, there's 1. Huh. So I didn't need the a, but I didn't know that. Right? This was a safe way. All right. So therefore, y sub p of x is equal to a's gone. B is minus x over 4 cosine 2x. There's our particular solution. So it worked. By putting these x's here, we were able to find a particular solution. Right? Let me show you rule 2. Rule 2 is a little more complicated than rule 1. So let me try and work through it with you, and then we'll do some more examples. So rule 2 says, suppose that in your right-hand side, you've got something that looks like x to the n f of x. Maybe x squared cosine 3x, maybe x to the 4th, e to the minus 5x. We got a power of x multiplying something else. So this is the f of x. And it says, and a non-negative integer, all right, so you can't have your x to the minus 2, because those aren't allowed. Suppose further, right, that f of x can be obtained from y sub h. Oh, This is telling me right here and now, I can't use rule 2 until I know y sub h. So if you're going for a particular solution, the first thing you got to go for is y sub h. You have to go for it anyway. If you want a general solution, it's saying, get it first. Because you can't talk rule 1 and rule 2 unless you got y sub h in front of your face. All right. So we're saying, if this is contained and obtained from y sub h by specified values for the arbitrary constants, right? So perhaps then, right? Suppose then that the y sub h looks like the function. Y sub h of x for that first is a cosine 3x, b sine 3x, right? I'm going to put an x in here, and I'm going to put an x squared in here. No, that wouldn't happen, okay? All right. Suppose these terms are in your y sub h. You would also have these ones. So if this came from the y sub h, you can't just have those. These ones would also be there, coming from a pair of repeated complex roots, right? So visualize that. Let's say, all right, if this term in y sub h results from a root of the auxiliary equation of multiplicity k, all right, so we're saying, yes, this guy can be obtained from here if I put 0, 0, 0, and 1. That would get me that guy. Not all of that, just looking at him, right? Now we said here, the roots were m is equal to plus or minus 2i, and but, no, 2, but 3, 3i, plus or minus 3i. All right, back on track. It says, if this term in y sub h results from a root of the auxiliary equation of multiplicity k, so here the multiplicity is 2. Each of these guys is multiplicity 2. Then corresponding to this guy. So now we want to write down what the y sub h is going to look like for him. As assume a part of that thing is put a constant in front of it, like you would have done if you had been using rule 1. That's what rule 1 would have said. Rule 2 says, no, you put in addition x to the k, another x squared. So you'll be starting then with x to the 4th. Right? That plus a constant now multiplied by linearly independent obtained by differentiation, but do not include terms that already are the y sub h. So there would be my start for this one, and this is the y sub h. So I start with that one, and now I start differentiating. If I differentiate this, I'll get x to the 4th sines. I need those. B, x to the 4th sine 3x. If I differentiate this, I also get x cubed cosines. I need those. C, x cubed cosine 3x. All right? If I differentiate this now, I get x to the 4th cos, that's back. But I get x cubed sines, I need those. X cubed sine 3x. Done with him, done with him. Now on to him. Differentiate this guy. You get x squared cosines. Oh, they're new. E, x squared cosine 3x. I'm going to differentiate this also. I'm going to take this one over that one. That's x cubed sine. Gotcha. You're done. Now you differentiate this one over that one. X squared sine. That's new. Need this one. X squared sine. If I take this one times the root of that one, that's x. No, I just did that one. This one times the root of that one, that's back to that one. So you're done. Now I differentiate this. X squared sine. Gotcha. This one times the root of that one, x cos. Ah, no include. He's already here. And the same thing down here. No new terms. So all of those would be predicted for this right-hand side if this is in the y sub h. You'd have all these as a part of your y sub t. So getting the idea again, it says, cover up any power. Look at that. Ask, can you get it from the y sub h? If the answer is no, then it's rule 1. do just what you know. If the answer is yes, then you have to start with the ax squared coast like you would with rule 1, but then you're going to bump it by x's. And the bump is by the multiplicity of the root that gives rise to that guy here. Got it? All right, let's do a couple more examples just to reinforce. So let's do the fun. I don't want to keep substituting and substituting, okay? And setting up these equations. That you've got to do. Get used to it. But I'm going to be lazy. You can't. So let's simply put some examples on the board and list what the y sub p should look like. Right? So here's the first one. Y double prime, 2y prime, plus y, x squared, e to the minus x, plus 2x. So what all the question is what is the form? The form of y sub p for undetermined coefficients. That's all I want to concentrate on. Rule 2 says you can't do it until you know the y sub h. So look at the auxiliary. Auxiliary. Equation is m squared, 2m, and 1 equals 0. M plus 1 squared, m equal to negative 1 and negative 1. Therefore, y sub h of x, a general solution of the associated homogeneous equation is c1 c2x e to the negative x. Now let's get y sub p. We'll look at that term, and we'll look at that term, and we'll add the results together. For this one, we cover the x squared. You ask, can you get this by specifying the constants in the y sub h? And the answer is yes. Put a 0 there, put a 1 there, and therefore you get this. Which means that you do not put ax squared e to the negative x. That's what rule 1 would say, but we are in rule 2 because that is in here. Rule 2 says, no, you have to bump that power. How much? Answer, the multiplicity of the root that gave rise to this guy. It came from here, the multiplicity is 2. This now starts with 4. There's your start. And you start differentiating this. Every time you get something new, include it, but don't include anybody that's already here. I think you'll agree, you differentiate this, you're going to get some x cubed e to the negative x's. Differentiate this, you're going to get some x squared e to the minus x's. You differentiate this, you're going to get x e to the minus x, but you've got them there. There's the 3 terms for y sub p for that term there. Now we have to go for this guy. We put a constant in front. Well, first of all, we ask. Don't forget to do this, okay? I've seen this happen so many times. 2x cubed. I put my hand over the 2x cubed. What's left? Answer, don't say 0. 1. What's left is 1. And so you ask, can you get 1 here by specifying C1 and C2? And the answer is no. Therefore, it is not rule 2, it is rule 1. And rule 1 says simply put a constant in there, right, and start differentiating. And therefore, you will get these terms. All right. Now, what we should be doing, if we're actually finding it, we would pick all this up, we would differentiate it twice. We would pick it all up, we would differentiate it once, we would pick it all up, put it here, and then we'd equate coefficients and get 4 equations or 3 equations eventually in A, B, and C, and 4 equations in D, E, F, and G that you would solve. All right? Second example. Y double prime plus 9y is equal to 3x sine 3x plus x squared e to the x. Do I really want to do that? Cosine 2x. I don't want 3x. All right, let's do that. We need the y sub h. You should by this time be able to say it is c1 cos 3x, c2 sine 3x. Oh, let me put that, I had a reason for that. Put that 3 back in again. All right, y sub p. We will look at this one and then we'll look at them separately and add together. For this one, we cover the 3, we cover the x. And we look and say, can you get this from the y sub h? And the answer is yes. Therefore, rule 2 is in play, right? Rule 2 is in play. Which means that we don't put ax sine 3x. This power next is going to have to get bumped. Should perhaps put in here, what was the m value? Plus or minus 3i. Right? So since the multiplicity, how many x's we put here, is dictated by the multiplicity here, the multiplicity of each is 1. So I'll put on 1 more x and make that an x squared. Now we'll differentiate and see what we get new. Differentiate, you get x squared cosine 3x's. That's new, I've included. If I differentiate this, I also get x sines. I need those. X sine 3x. That takes care of that guy. Now I differentiate this guy. This one times that one is back to that one. But this one times that one, that's x cosines. I need those guys. They're new. That takes care of that one. Now I differentiate this. I get x cos, that's already there. I get sine, but they're already in my y sub h. I'm done. And this one won't give anything new either, or something in the y sub h. That takes care of that one. All right. On to this ugly looking thing. I cover the x squared, and I look and say, hey, is this in my y sub h? And the answer is no. The cosine is, but not the exponential. It is not, therefore, rule 2. It's rule 1. So away we go. We're up to e x squared e to the x cosine 3x. Now we start differentiating. Now you got a triple thing here, so you got a triple product rule, right? So if I take this one times this one times that one, that's nothing new. But if I take this one times this one times that one, that's new. That would be up to f x e to the x cosine 2x. I also take this one times this one times that one, that's going to be sines. That's g x e x squared e to the x sine 3x's. So I now have differentiated that one. Now let's talk about differentiating this one. I'm going to get, if I differentiate that one, nothing new. I would get, if I differentiate this one, an h e to the x cosine 2x. Now I got to differentiate this one. That's going to give me an I x e to the x sine 2x. I think I finished with that one. Now this one. That differentiated, nothing new. This one differentiated. X sines. I got you. This one differentiated. x cosines. X cosines. Did I forget something here? Oh, great. Where does that one come from? Wow, I forgot where I am now. Ah! This one gave rise to those two. Then I'm checking this guy. All right, that's okay. All right. So now we're taking care of this one. We're going to have x sines, got them. I'm also going to have x squared cosines, got them. All right, so I've taken care of you. Now you, differentiating, okay, it's going to give me e to the x sines. I don't have any e to the x sines. J, e to the x sine 3x. This one's under that one. This one's under that one. That's just plain cosines. Cosines plus. No, there's not just plain cosines. That's it. This one's under that one. That's it. Back again. All right. So now you're gone. Now this one. No different here. We differentiate. That's e to the x sine. Gotcha. And then we differentiate this one. X e to the x cos. X e to the x. Gotcha. All right. This one. Differentiate e to the x cos. Gotcha. That's it. See, I hope I didn't leave anything out. All right. So there's the wife's P for that particular ugly looking right hand side. I would not relish differentiating this twice, and putting it here, and equating coefficients. That would be nasty. All right, put that tutorial in, or video.